Good. Good. Okay. Come on. Okay. Hello, everybody. Um, Today we're going to open up a new chapter in our class, and that is chapter 3, uh, memory hierarchy performance. Now, when we say computer memory, um, we have to be aware of the fact that in any computer, we do not have a monolithic type of memory. So it's not like you have a memory and everything is the same and it's uniformly designed and so on. But rather, we have a hierarchy. Okay, such that we have something pretty much like this. So we have the CPU. Oh my God. This is the CPU where we have registers, and yeah, then we have the cache. Then we have the memory bus connecting with the main memory, which is bigger than the cache. And then we have a connection with uh, the I/O devices, including disks, secondary storage. So this is the register reference, the cache reference, the memory reference, and the disk reference. So it's like having a triangle like this, where you have the CPU registers here, then you have the cache, then you have the main memory, and you have the disk or so secondary storage. Okay, the size is growing as you go downstairs. So, right, the disk is bigger than the main memory. The main memory has a bigger capacity than the cache, and the cache obviously is bigger than the um, uh, capacity of the CPU registers, whereas the performance goes in the other direction, um, in the opposite direction, right? It's clear that the CPU registers are the fastest, and then the cache, and then the main memory, and then the disk. The cache itself is um, hierarchical these days. Namely, you have caches on different levels, but we will discuss this in the following weeks. As of now, we will consider the cache as being on just one level, uh, because the how the cache relates with the CPU and the main memory is the same way in which a lower level of cache interacts with the higher level and with the lower level of cache. So it's the relationship is similar. It's the same. I mean, the same principles apply here. So yeah, um, it's for educational purposes, for now, we will stick with this one level of cache only. Okay, so um, as of now, we will concentrate on cache, this mechanism of cache memories, and we will discuss them. And as such, we will start with 3.1, which is map. It's related to mapping techniques. Why are they so important, or what is mapping? Well, first of all, the CPU wants to read and write and stuff, and that stuff comes under the form of words, right? Whether we are talking about instruction or data, these come under the form of words, right? One instruction is encoded in one word. Now, one word, one word can be um, um, represented on 2 to the power r bytes. For instance, the instruction word and data word in ARM processors are on 4 bytes, namely 32 bits. So that's one example. So that's how it works. I mean, when the processor needs to read instructions and then execute them. So the processor needs to read instruction words, one word at a time. So that's what processors are eating, so to speak, words. And it is the same thing for data words, right? So some instructions, when some instructions are executed, the processor will need to read or write words. And that's one difference between instructions and data. Uh, when we are talking about instructions, the processor will only read them in order to execute them, right? When the processor works with data, the processor can read or write such words. Now, that's an important, distinction. uh, Reading and writing, that's one, and then instructions and data. Now, um, the idea with the cache is that the processor, when the processor wants to read or write words, um, it goes to the main memory if we don't have a cache, right? But the main memory is kind of slow, at least when comparing the speed of the main memory with the speed of the internal registers of the CPU and the CPU as a whole, right? So we need something that is quicker, that goes quicker, that has more speed, um, a better memory in that respect. But these memories are obviously they are not cheap. They are on the contrary, they are very expensive. So we need a smaller quantity of memories that goes between the CPU and the main memory. On the other hand, remember one of the principles that we were discussing um, uh, in one of the last weeks, I don't know, in one of our previous lectures, and that principle is the locality principle, which states as a rule of thumb that in 90% of the time, the processor executes pretty much 10% of the instructions. So there is a small subset of instructions in a program that are very frequently used, right? And the other instructions are not that used. Okay, so it makes sense that we put this memory, smaller memory but quicker memory, between the CPU and the main memory, such that the CPU will search first, will search in this memory. This memory is called cache. And I think it's one of the few, if not the only, computer term which comes from French. Cache comes from the French caché, which means hidden. So because it's right, it's hidden. It's not in the main memory. It's hidden such that the CPU will have a quicker access to data and instructions in the cache. So that is the idea, right? Whether we are talking about instructions or data, the CPU needs to keep the instructions or data that are more frequently used in this smaller but quicker memory. Okay, that's why we have um, mm, in some systems we have unified caches or split caches, which means that in unified caches you put in the same cache memory instructions and data. In split caches you have specialized caches, a cache only for instructions and a cache only for data. So instructions and data are separate. or separated, right? You have one cache for data, one cache for instructions. Now, um, what happens if the processor doesn't find what it needs, be it instructions or data, in the cache? When it finds it, we call this fortunate event a hit. Instructions or data found in the cache, and miss when the instruction or data is not found in the cache. Okay. Now, when you have a hit, that's perfect. You have quick access. When you have a miss, well, that's going to be a problem because it's such an access, memory access, read or write, whatever, is even slower than in the situation where you don't have a cache memory. Why? Because the CPU will first try to read or write in the cache, only to find that the word is not there, and therefore it needs to bring and then it goes to the main memory and works with the main memory. But at the same time, it needs to bring that word in the cache. Why? Well, to comply with the locality principle, because if that word is accessed now, it is very probable that it will be accessed in the near future. So it needs to be placed in the cache. Now, we will come back to all these mechanisms and discuss them thoroughly, but where I wanted to bring the discussion for now is this. We need to bring information from the main memory inside the cache, which means that the contents of the cache is a subset of what it is already present in the main memory. So some subset of words from the main memory are in the cache. Now, this brings another problem. When you read, that's not going to be a problem. A subset of what you read is from the main memory is in the cache, so you can read it uh, quicker, faster. So that's it. There's no problem. But when you try to write, what happens if you write only in the cache? Well, it means that you have basically the same word with the same address in the main memory and in the cache, but the contents of that word are different, which means that you don't have what we call cache coherency. Nonetheless, the discussion right now revolves around this thing. We have to bring info and words, missing words, words that the processor needs from the main memory and put them in the cache. Now, to do this, we are using some sort of packaging of this data. Okay, and that package comes under the form of a block, right? A block is group of words a group of words that have contiguous addresses. So in other words, it's like to, uh, you know, bring an analogy, although I do not condone smoking, but it will relate to smoking and cigarettes. So a block is like, I mean, the bite is like a cigarette, okay? And a pack of cigarettes is like the word. The word, right? One word consists of 2 to the power of r byte. So byte is a cigarette. The word is a pack of cigarettes. Then the block is, I don't know the English term, is like the box of um, packs of cigarettes. So that's the block, right? Um, so a block consists of 2 to the power of p words. Um, and when information the information is exchanged between the main memory and the cache is exchanged only under the form of such blocks, right? So the let me give you this scenario which relates to reading without losing generality. The CPU wants to read an instruction which is in some word, I don't know, a word, but uh, this access in the cache comes as a miss, so the word is not in the cache. Therefore, the CPU will read the word from the main memory, and at the same time, in parallel, right, it will bring the block which contains the word, the missing word, will bring the entire block in the cache. So that's how the the mechanism works. Um, how we map these blocks from the main memory inside the cache, well, this how is answered by the mapping techniques, right? So that's why we have mapping techniques, to know how to map the blocks from the main memory in the cache. When you bring a block of words from the main memory, you have to know where to put it within the cache. So we begin our discussion about mapping techniques with 311, and that is direct mapping, which is the simplest way of mapping blocks. In order, to explain this, let's consider this scenario, or this formalism. We denote M2 is the main memory, and M1 is the cache, because it's closer to the CPU. And we denote, we are we have these and 2 to the power n, 2 to the power n blocks in the main memory, and so on. J. So the M2 size, so let's put it like this, size of M2 in terms of number of blocks is 2 to the power n. And for M1, for the cache, we have something like this. So the size of M1 is 2 to the power M blocks. Obviously, N is bigger than M, right? Because the main memory is much bigger than the. And as I said, each block is 2 to the power P words big with 2 to the power R bytes for each word. Okay, so in this context, the index, the number of the block, which is the index of the block in the cache, which corresponds to block J in the main memory, is given by this formula. So Y is J modulo 2 to the power n, which is the cache size as number of blocks. Let me give you this example. This example has M2 with N5. So N being 5 means that I have 32 blocks. 2 to the power 5 is 32. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31, right? So these are right 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, and 31. Okay, so n is 5. Good. So this is n2. This is the, you know, the map of blocks um, in the main memory. Um, let's see. The cache M1, right? So it's no. No. Okay, so it's 0, 1, 2, 3, 4, 5, 6, and 7. So M is 3. Now, if we need to map, let's say, block 0, where are we mapping block 0? Of course, we are mapping it here. right? It goes here. Who else goes here? 8 is mapped here, right? Um, 16 is mapped. 24 is mapped, right? So these 4 blocks are all mapped here at index 0 in the cache, right? When you bring these 4 blocks, they can only be, put here at this index in the cache. Okay. Now, for instance, let's say we take 12, right? Block 12. Well, 12 modulo 8, right? Which is 12. This is j, right? This is j, and 8 is 2 to the power 3, right? So this is 4, right? So you put it here, right? Check this one. It goes here. Okay, so it works this way, and you can look at it from this perspective. Now, if you write it as an address, right, the number of the block in the main memory is 12, right? Let's take this example of 12, and it's on 5 bits. The address is on 5 bits, right? Because yeah, so that's the number of the block is given by this address on 5 bits. So it's 01100. That's 12, right? This is 12, and right, this is 12. So M is 3, right? This is M 3. These three bits. What is the value of this? Oh, sorry. Obviously, it's 4, right? It's 4, which is the index, the same index that we were talking about. Now, as you can see, many blocks are from the main memory are mapped on the same, so they are in competition. What happens if we need words from this from this block, block 0, but we also need words from block 16? What happens? Well, these blocks will, so to speak, kick each other's toes in the cache, because um, they will they will be written one over the other, such that okay, only one of them can be in the cache at one time. So, well, in such a case, we need to, when we need, for instance, when we need 16, block 16, some word from block 16, but block 16 is not in the cache because that index is occupied by block 0. So we need to throw out block number 0 and bring block 16 in the cache. Now, to throw out, to put it or to update a block that is thrown out of the cache in the main memory, we need to know what is the correspondent, where to put it back, in other words. So we need to know the block that is over here at index 0, or the block that is at index 4, to what block from the main memory it corresponds. Because only from the index you don't know. You have something at block 0, so maybe it corresponds to block 0 or block 8 or block 16 or block 24 in the cache. In order to uniquely identify the exact location in the main memory of a cache block, you need to have a field that is called a tag field. So this is the data part of the cache, and at the same indexes you'll have what we call a tag, right? This is the tag 0, 1, 2, 3, 4, 5, 6, 7. Now, who is the tag? It's very simple. Is the part of the address, the block address that remained after you clipped this part which identifies the index. So you'll put here a 0, 1. This way you will know that this block corresponds to block 12 because it's at index 4 and tag 0, 1. So you can reverse engineer this, right? You reverse it. So it's tag, which is 0, 1, and then it's the index 1, 0, 0. So this brings you back to 12. So you know this is 12, right? So this is the mechanism of identifying the correspondent in the main memory of any cache block. Good. Now, um, after discussing and knowing all these, we can specify the exact address word, and it is like this. So what is the structure of an address word in the processor? So you have this word offset field on P bits. But if you have a distinct address for each word, for each byte, sorry, if you have 2 to the power r bytes per word, then you will have, in such a case, you will have a byte offset. Not all processors are addressing each and every byte. There are processors which are not doing this. Some are doing it. If they do it, they have a byte offset, right? Because they need to identify each and every byte. To this end, we need to, and each and every time we will state which is the addressable unit. In other words, which is the unit of information of bit groupings, so to speak, which have a distinct address, right? A unique address. If you have a unique address for each and every byte, the addressable unit for you is the byte, and you will have a byte offset. If the addressable unit is the word, then you don't have a byte offset. Well, there is actually a situation where the addressable unit is the byte and you don't have a byte offset. And that is the case of one, I'll put it here. So if you have one word is 1 byte, right? It means that one word is on 2 to the power 0 bytes. So R is 0, which means that there's no byte offset. Or in other words, the length of the byte offset field is 0, right? Good. Now, then you have the index, which is on m bits. M, remember, 2 to the power m is the size, as number of blocks, the size of the cache. And one block is actually considered a cache line. So you have a line of cache, that's one block. And then you have the tag, which is on n minus m bits. Okay, so that's the address word for direct mapping. Now, I will take an example. I think it's an illustrative example. Example 1 for today. And the example goes like this. So we consider a memory, a main memory made of 2 to the power 24 words. And one word is actually 1 byte. In this example, one block is 4 words. So one word is 1 byte, which means that we don't have a byte offset, right? And the addressing, okay, so the addressing unit is, you can say that is the byte or the word. It's correct either way because the byte is the word. So this cache for this memory system, we consider a direct mapped cache of the size with data size um, 1 kilo block, which means 2 to the power 10 blocks, right? Good. And in this, for this cache, we assume that we have a small program which consists of just 3 instructions in assembly language. This program is, well, in real life it's not like this, because in real life normally these instructions will have contiguous addresses, but nonetheless, let's see, just for the sake of, you know, learning how these caches work, we are hypothetically admitting that the first instruction is at address 8192, and the code of the instruction is a hypothetical code nonetheless, 230. And then the computer goes at this address 4100, 4100, only to execute the instruction with the hypothetical code 2715, and then goes at the address 12292 and execute the hypothetical instruction, an instruction with the hypothetical code 107. Let's consider this. Right. This is an hypothetical, obviously a hypothetical situation. Now, let's see about the main memory, M2, in our case. Now, first of all, what is the size of M2? Now, the size of the main memory is 2 to the power 24 words. Now, the word is the byte, so it's, but, right, so one block, well, in this case, 2 to the, because one word is one byte, is 2 to the power 24 bytes. So it's 2 to the power 4 times 2 to the power 20 bytes. 2 to the power 10 is kilo. 2 to the power 20 is mega. So this is 16, 2 to the power 4, 16 megabytes. Right? Good. On the other hand, if we are to consider the number of blocks, is 2 to the power 24 words divided by 2 to the power 2, that is words per block. That would be 2 to the power 22 blocks in the main memory. Good. So this means that we have something like this. We have M2 and here we have the address and the block number. So the first block, in the first block, for each and every block, we have four words, right? So here is the word, or the byte is the same thing with the distinct address 0, right? 1, 2, and 3. These are the addresses of these words, but I'm going to delete it because uh, I don't want you to be confused and consider that this is the contents of these locations. No, it's not the location. So we have addresses starting with 0, which means this word has address 0, 1, 2, and 3, but the contents are different. And then the address starting from 4, meaning that this is 5, address 5, word with address 5, address 6, 7, and 8. That's block 7. 8 is here. So I'm only putting here the starting address. Right, we have addresses from 0 to 3, from 4 to 7, from 8 to 11, and so on. I'm only putting here the starting address, right? And then you have other 3 words. You get the idea, right? And so on and so forth. Now let's see this block 2 to the power of 10 minus 1. So as this is this guy. This guy starts with an address, it's simply the starting address is 4 times this value. So this is 4000 92, right? And then you have this block is 4096, and then you have 4100, and we know this address. So this is 4100, 4101, 4102, 4103. But we know that at this address we have an instruction with the hypothetical code 2715, and it's placed here. In all the other words, we have different codes or values, but we don't care about them because we don't use them in our example. Right, so let's see, um, you know, another block or farther away. So it's 2 to the power of 11, right? It starts with 18192, and we know this address because it contains this instruction with code 230. Again, we don't care about the others as we do not use them. And it's, so on and so forth. So 2049, it's going to be 8196 here, and so on, right? Good. Um, let's see, about 3 times um, 2 to the power um, 2 to the power um, 10 plus 4. So it's 10 to the power 4, to the power 10 is 1024, right? Times 3. So it's 12, 1703. Um, yeah, yeah. Yeah, let's put it right there. I guess this is a good example, nonetheless. Um, yeah. So let's put it plus 1, right? So that's 3073. Let's consider, yeah, because yeah. So 4 times this, that's the address that we need. So it's 12,292. So that's the number of the block. Okay, so it's a good example because, right? So 12,292, 12. So I have 170 right here. And of course, it goes, right? So on and so forth. The last one will be block number 2 to the power of 22 minus 1. We already discussed this, right? When we compute uh, com the size of the main memory in terms of blocks, right? This goes from 0 to 2 to the power 22 minus 1. And the starting address here is 2 to the power 24 minus 4. So it's 4 times this quantity. So we have a visualization of these words in the main memory, right? The words that the CPU needs to read because they are considered as, instructions. Now, the cache, so the address word, right? Let's see the address word here. First, we have this block, this word offset, right? No, let's put word offset. It's on 2 bits. Why? Well, because one block is 4 words, so it's 2 to the power of 2 words. So, these 2 gives the size of the word offset. Now, the cache size is 1 kilo block. So the number of lines, the number of blocks, m, right, is, how big is m? Because this is the number of blocks. 2 to the power m is the number of blocks, right? It's 2 to the power m. So who is m here? 1 kilo block is 2 to the power 10 blocks. Right. So m is 10, right? That's why the index is on 10 bits, right? These 10, right, comes from here. That's why it's 10. And we know the size of the address word because we need to have distinct addresses for each and every word. One word is 1 byte. Each and every byte is the same thing in our case. And we have 2 to the power 24 words or bytes, whatever. So this means that the size of the address word is 24 bits. So this is 23, this is 12. So when you have 24 minus 12, that means you have a 12-bit tag. So this is the address format. And now let's see the cache. Okay. Okay. So each and every cache has a valid bit. Why? Because initially the cache is empty, is considered empty. It's a 1 bit. Then you have the tag, which has to correspond to this tag size on 12 bits. And we have the data part. Data part, which consists of 4 words. So on each line, you have a block, word, 4 words, right? This is block 0, block 1, block 2, block 3, so on and so forth. This is block 1, 0, 2, 3, right? Because we have 1024 blocks, which means 1 kilo block. So you see, this index, these bits will be used as index in the cache, like an address in this cache, right? So you take this tag and compare it with this tag here, and if they are equal, right, it means that you have a hit, right? So it goes like this. You have this tag, 12 bits. Now these are 10 bits. So you compare this 12 bits against these bits, and if the valid bit is 1, you have a hit. Okay, so that's how it works, but I'll show you in more detail for other examples. Let's settle for this for now and see what we're interested now is where these words are mapped, the words from our hypothetical mini program here. Okay, so let's see. Oh, and data is uh, mm, 4 bytes, right? 4 words. Each word is 1 byte, so we are talking about 4 bytes here. 1 byte is 8 bits, 2 to the power 3 times 2 to the power 2. That's 2 to the power 5 bits, which means 32 bits. Good. Now, let's see the first line of program, right? So we are talking about address 8192. 8192 is actually 2 to the power of 13. So 8192, right, is 2 to the power 13, and all the other bits from the address are 0. So to the power of 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and 0. And the others up to, because there are 24 bits, are also zeros. So this is the address, but we know the address format, right? These two are the offset, right? And then the next 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, these bits are the index. So this is the offset, this is the index, and this is the tag. So, in other words, where is this block going to be mapped? I mean, this word. Well, it will be mapped with the entire block, with the entire block that has block number 2048, right? It will be mapped where? Well, let's look at the index. It's 0. And that is because we have this 2 to the power of 13 modulo 2 to the power 10, which is the size of the cache. That's 0, right? So it maps at address at index 0. So the value will be put on 1. The tag, as we see, is 2. This value is 2, right? And the contents of the first word is 230, and the others we don't care about. Okay, we're not discussing it, but we're talking about the contents of this block, right? Now let's see 4100, right? That is 4 plus 2 to the power 12 That's 4100. So you have something like this instead. 2 to the power of 12, that's a 1 here. And a 4 is going to be like this. That's 4 plus 4. So the offset is this, the index is this. So this word goes at index 0. And you can clearly see that this block is within, this word is within block 101025, right? With modulo 2 to the power 10 is obvious, 2 to the power 10 is 1024, so obviously is 1. It's the same thing. I've done the same thing in different manners, namely observing that it goes at index 1. The tag is, as we see here, the tag is 1, right? And in this block, we are only interested in the first word. We know the contents is this code. And the other ones, we don't care about. We're talking about these words, but we are not interested in these words. Okay, and then let's see the last instruction, which is at this address. So it's 3 times 2 to the power. So it's 2 to the power 12 to 92 is 2 to the power 13 plus 2 to the power 12 plus 4. You can see it's because it's to the power 13 is 8192 plus power 12 is 4096 and then 4, right? So it's 6 plus 6, that's 12, 9, 2, and 12, right? So you can see how to decompose this number in power of 2 factors. So it's 12, 292. I mean, you know what I'm doing here. I'm representing it in binary. That's what I'm doing. So it's 0 on 0, 2 to the power 13, 2 to the power 12, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 1 plus 4, 0, 0. And this is the offset, this is the index, and this is the tag. Now, the index is the same because 12, 292 modulo 2 to the power 10 is 1, right? Yeah. No, actually, it's not like this. Yeah, I made a terrible mistake here. I have to put here the block number. So where's the block number? Is this guy? This is the block number. So it's 3073 modulo 1024. That's 1. Okay, so that's why it has the index 1. So when the processor accesses this new block, this new word, it has to put it where? At index 1. So it will throw out what was previously at index 1 and put the valid remains valid, but the new tag is 3, as you can see here is 3. So 3. The new value here will be 170, and of course these new words here that come with this block, right? But we are not interested in these words. So as you can clearly see, one word, these words which belong to blocks that are mapped at the same index within the cache will kick each other toes, as I said. And this is a huge impediment for performance sometimes, especially when we are talking about the so-called miss rate, which is obviously 1 minus hit rate. So when you have memory accesses, what percentage is a miss, a cache miss? Obviously, that's 1 minus the hit rate. So we aim at minimizing the miss rate, but if you have words that are eliminating each other from the cache because they belong to blocks which are mapped at the same index, uh, you'll have a lot of misses, right? Because you need the first word, and then you need the second word, and so on, and then they will kick each other, kick each other's butt, so to speak, from the cache. You'll have a lot of misses. That's not good for performance. Now, I'm going to give you a new example. Real world example. Because as of now, we only talked about, hypothetical situations and architectures and so on. Now, I'll talk about um, 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 an embedded processor. So this is a cache that is part of a system built around the intrinsically. That's a company, intrinsically. Fast, fast math processor. This is an embedded processor designed for applications with intense mathematic operations and instructions. So it's an embedded processor. It has a MIPS architecture, which means that it is a load store machine. We already discussed about load store machines in our previous lectures. These machines that have specialized instructions for working with the memory, loads and stores, and only these instructions are having access to the memory. The words, the addresses are on 32 bits. And um, the addressable unit is the byte. So each byte has its own address. is it has a 12-stage pipeline, which is, well, it's a lot of, it means a lot of stages, but this is not uncommon for floating point mathematical operations. So that's why it has so many pipeline stages. It has a separate, or what we, the term that we used before was split um, instruction and data caches. All right. And each cache, instruction and data, is 16 kilobyte or words with 16 word blocks. Okay. Now, this means that, okay, so it has a 32-bit address word. So the address word is like this, right? Good. Um, so each cache is 16 kilobyte big with, so 16 kilobytes. This means 2 to the power 4 times 2 to the power 10 byte, right? But at the same time, we know that we are talking about 2 to the power of, so we are talking about these many words. So this is 2 to the power 12, right? Words. So the same size, right? This is the cache size in terms of bytes and in terms of words. Now, if we make this division, we will find the number of bytes per word. So, right. So it's 2 power 2 bytes per word. So we are talking about 4-byte words, which means that one word has 4 bytes. So 2 to the power of 2, right? Which means that, okay, I have here, right, this byte offset on 2 bits. And then we have the word offset. So how many words do we have on one block? So we have the information here, which means this means 2 to the power of 4 words per block. So we will have 4 bits for the word offset, right? These 4 come from here. Come on. So right from here, we're talking about these, right? And these two come from here. Now, let's see the index. Well, the index, um, to compute the index, we need to know the size of the block. So how many blocks do we have on this direct mapped cache? How many blocks? Because it's one line, one block, one line. So we need to address all these lines with the index field. So we know the size of the cache in terms of bytes or words, but we have 16 word blocks. So it means that, cache size divided by um, 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 block size, right? So cache size is 2 to the power 12 words. Block size is 16 words, so it's 2 to the power 4 words. So this gives us a 2 to the power of 8 blocks. So we have an 8 bit index field from bit 6 to 13. The size, as I said, is 8. Right? And this is the explanation for 8. And the rest, obviously, is the tag. So the tag is what remains all the time. So here we have 12, 14, 14. So 14, it's what remained is on 18 bits. Okay, so this is the address word. Now let's see the structure of the cache. We have something like this. This is line 0, 1, whatever. 2 to the power of 8 lines, so it's 256. So it's from 0 to 255. Okay. Tag. This is the valid on 1 bit. The tag on 18 bits. And the data. Let's see the size of the data in bits. So it's 16 is 2 to the power. Let's make the calculations here upstairs. So it's data. It's 2 to the power 4, 16 words per block, right? Times 2 to the power 2 bytes, right? So one word is 2 to the power 2 bytes. So it is 2 to the power of 6 bytes, right? Data, 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 um, data block, the data for one block. So it's two, I don't know how to put it. It's right, the amount of data here, the amount of data per block or per cache line, right? So 2 to the power 6 bytes, but you can put it inter or as this 2 to the power of 6 times 2 to the power of 3 bits, right? Because 1 byte is 8 bits, 2 to the power of 3 bits, so it's 2 to the power of 9 bits, which means, right, which means 512 bits, right? So that many bits. Okay. Now, if you take the index field, these 8 bits, you can use them as index. You take these bits and use them as index in this table, this cache. And then if when you address this, the CPU does it, compares these 18 bits with these, okay, and makes, right, sure that it's valid. So it's a hit here. And we have, right, we have here, let's do this thicker lines. Here. Okay. Like this. And you have, you know, word 0, word 1, and so on. Right? So this is word 0, word 1, word, and so on and so forth, word 14 and word 15, right? In the data part, and these words are multiplexed with a 16 to 1 multiplexer, right? So this word is on 32 bits, this word on 32 bits, and so on, right? This one is also on 32 bits, and this one also on 32 bits. And this will be the data, one word, data, to, it goes to CPU, the CPU, and these 4 bits are used to select one of the words, one of the 16 words that are multiplexed here. Okay, so that's how the selection is performed in this real world example of a cache. This intrinsicity. Now, I'm going to move forward because we have 10 more minutes, and Discuss section 312, set associative mapping. Now, as you saw in the first example for today, um, the problem with direct mapping is that you have these situations where many or several blocks that are used by the program or the CPU uh, when executing some program. Um, these blocks are mapped at the same cache index, and is this conflict that generates a lot of misses. Now, the idea at set associative mapping is to associate a number of blocks for each index, because right now at the direct mapping technique, you have one block for one cache index. Now, the idea for set associative mapping is to have multiple blocks, or to put it in other words, k blocks, where k is 2 to the power of s blocks associated to the same cache index. So that is the idea. So when when s is 0, it means that k is 1. So you have one block associated at the same cache index, which is exactly the direct mapping case. Now, obviously, this is a generalization of direct mapping by allowing, as I said, multiple blocks to be associated at the same cache index. So um, in this um, you know um, technique with this technique, uh, M2 is the same, so the same as before. So you have M2 from block 0 and so on and so forth, M to J, M2 to the power n minus 1. That's M2. And M1 this time is M1. So you have these indexes, right? M1 of 1 and so on. M1 of I prime. This is a new index. And M1 to the power M prime minus 1, where M prime is M minus S. This means that I prime, which is the index associated where the block from the main memory is mapped, will be J, where J is the index of the block in the main memory, modulo 2 to the power of M prime, meaning M minus S, or same thing as saying modulo 2 to the power of M prime. Now, this is kind of very abstract and stuff. So I'm going to give you the same example of M2 where n is 5, where you have this 32, right? This is the block number, right? This is block number 0, and so on. I'm not going to draw it again. 12, we talked about 12 in particular, so we'll take it again, and 31, right? I'm writing ugly here. So yeah, it's like this, and this time you'll have M1 with the same 8 blocks as before. So M is 3. So you have 0, 1, 2, 3, 4, 5, 6, 7. These are not the actual indexes in the cache, the ones from above, but we are just putting numbers to see that we have 8 blocks. Instead, we, make these sets 0, set of blocks that are associated to the same cache index. Set 1, set 2, and set 3. So yeah, it means that S is 1. Why? Because we associate 2 to the power of S, 2 to the power of 1, namely 2 blocks at the same index. We are making sets of 2 blocks. That's why S is 1 in this example. So the new index here is M prime um, um, is M minus S. So that's why we are going from 0 to 2 to the power of M minus S, 3 minus 1, 2 to the power of 2 minus 1. So our new indexes are 0, 1, 2, 3. Okay? And we have the tag also. Okay? Now, where are we putting block 12? Well, we have 12 modulo 2 to the power 3 minus 1, M minus S. This is M prime. So it's 12 modulo 4, which is 0. Okay? Which is 0. Which means that I'm putting 12 where? Where? Here. In set 0. In this block, it doesn't matter, actually. I can put this, right? I can put it here if that would be the case, right? So so it goes here in set 0, but it can go in the other block as well. Okay, because they are associated to the same index. Now let's see how this works in another way. So the address 12, right, is 01100 on 5 bits. So that's n. N. The previous m, the m was 3, right? But right now, the index is given by m prime, or m prime is m minus s, which means 3 minus 1, that's 2. So m prime is this, right? 2 bits, right? And the new tag is what remains over here. This is the new tag. Okay, so that's why the new index is 0, because we are only clipping these 2 bits for the index, and the remaining 3 are the tag. So if you are putting in these one of these blocks, let's say we put it in block 1 here, in set 0, the tag would be 0, 1, 1. See, 0, 1, 1 here. Okay. This mapping is also called two-way set associative mapping. Why? Because we have k is 2 to the power s is 2 to the power 1, which means 2. So k is 2, right? That's why it's called two-way set associative mapping, which means, as we saw, that two blocks are associated to the same cache index. Now, next week we'll take some example, a similar example, or similar examples for two-way set associative caches and see how they work. And look more thoroughly into these set associative mappings and understand them better, and then discuss the third way of cache mapping, which is full associative mapping, and of course other stuff related to cache. Hopefully next week we will finish everything related to caches. Okay. Now, thank you very much for listening to me today, and this very important lesson lecture about caches. Caches are very important, and it's important to understand the mechanism behind them. Now I'm going to stop the streaming and see you on Discord for a questions and answers session. If you have anything to ask, just please go ahead and ask me on Discord.